This one is going to be about predicting stocks. Specifically, I guess we're going to be using the Tesla stock to kind of as our example. But I would like to invite Aditya to lead your guys' next workshop on predicting stocks. It should be interesting. Aditya,
All
you can
right,
take
yeah.
it.
So, let's share screen real quick. Can everyone see? Yep, I think it should be good. Cool. Okay, let's get this started. So, a lot of you guys might be familiar with Tesla stock, right? Like, if you guys have been, not living under a rock for the last 2 years, you'll know that this stock has seen like some insane value jumps, right? Like in 2014, it was trading at around $39, right? And in 2019, it shot up to around $2,500. And then the stock was split. So they split it into, they basically made each value 400, and everyone who owned one share got 5 shares instead. So that was pretty nuts, and it was a pretty huge rally, right? And then it shot up again in 2021, back up again to 1,100, which is just absolutely insane, right? So it kind of just goes to show how the volatility of the stock market is kind of insane, right? Like literally anything can happen. Absolutely no one would have predicted this huge spike that happened just in the last year, right? So it would be awesome if we had some method, some way of predicting when these huge spikes might happen, or just predict stock prices in general, because that would make investing a lot safer. Like if you knew, for example, that the stock was going to dip from, I don't know, maybe like 718 to 686 or 563 in the next 2 days, that'd be helpful. You could sell the stock earlier and avoid losing money. And really, artificial intelligence can help us solve this problem, right? And it can help solve it in a really effective manner too. So, let's head over to the workshop 2 stock prices predictor thing. I'll link it into the chat. And for this one, it's going to be a little bit more complicated, but still pretty simple overall. So this time, we're going to have a bunch of different resources that you need, right? If you'll recall, last time we used a data set, right? We used the MNIST data set, which is built into TensorFlow to help us get our handwritten digit classification data. This time, however, the Tesla stock data isn't actually available on TensorFlow, right? This is third-party data. So if you'll recall, our first speaker, she mentioned a site called Kaggle. And what Kaggle does is that it curates datasets from hundreds and hundreds of different industries and presents them in a way that we can use it. So Kaggle has something called an API, basically a way that we can access their data. And they also happen to have a dataset that is based on Tesla stock. So to actually run this notebook, we need to download the Kaggle API file, and it's necessary to actually access the data from the cloud. And all you need to do is download this, and that's basically it actually. Just download this onto your computer, and we will help you guys sort everything else out. So pretty simple. Just click the file, click download, and yeah, pretty simple stuff. Right, and as you can see, this is literally just a username and password. Yeah. Oh, you need access. I'll quickly change this again. Yeah, anyone on link can edit. I'll copy it again and send it. Also, make sure to use your personal account, because school accounts do not work with this kind of stuff. Alright, cool. Has everyone downloaded the Kaggle API file, and is everyone on this link? I mean, given the sheer amount of cursors here, I guess it's a yes. Cool. So, same thing as last time. You guys can, sorry, whoops, added an extra cell there. So a couple of things here. You guys can either click File and save a copy to your drive and follow along, or you can just view this file as it is and watch as I make edits, whichever one you guys are more comfortable with. But I would recommend making your own copy and following along, since the best way to learn is actually doing things. Cool. I'm going to guess that everyone is basically done. So let's start things off. So you might recall that in the last time we used something called a dense layer, right? And dense layers are just the regular layers that we've been talking about for the last workshop. These are the things that take an input and give you an output. Pretty simple, right? However, when we're talking about predicting stocks, there's actually a slight problem here. What exactly do we use as our input, right? So you might recall the fact that for our input for the classifying dogs problem, right, we would pass in a picture of dogs, we would convert it, and then we would get a 0 or 1 as the output. For stocks, however, it's a little bit more complicated. Why? Because it's a different type of data, known as time series, right? Instead of having an attribute such as a dog or cat, it's based on the date. Like, for example, if we go over to the graph, on July 2021, the stock was 680.76. Right? On September, it was 732, and then it just keeps changing based on what the date is. The problem is that we can't pass in the date and get the value, right? Because this stock value is not even dependent on the date itself. Instead, it depends on a lot of other different factors. For example, it might depend on the revenue of the company. It might depend on the trading volume that day, which is the number of stocks that have been traded, right? So really, there are a lot of other factors influencing this. And one of the main ones is what the stock price was just one day before. And this is a really important concept to grasp. The stock price at any given moment depends on what the stock price was just a little bit before that, right? For example, this spike from $919 all the way to $948. The $948 value depends on this 929 value because you cannot predict a spike unless you take all these values into consideration. And it's the same thing if you're trying to maybe say what the weather was today, right? Maybe at 6 a.m. it was 25 degrees, then 18 degrees, and it kept changing like that throughout the day. In either case, the temperature at each time somehow depended on the temperature of the time before it. Because you cannot just have 25 degrees and immediately go down to negative 40. It needs to be dependent on some way to the value that comes before it. And that's why this is called time series data. And the problem is that neural networks only take in a value at a constant period of time, right? Like, for example, you can only pass in one array of numbers. And what happens is that every single time you run the neural network, it has no way of taking in its last prediction. Like, for example, maybe we passed in this value, right? Like 4 p.m., we wanted to know what the price would be at 4 p.m. on, well, this is actually yesterday, right? 4 p.m. on a Friday. If we pass that in, it would return any random value. And it has no way of knowing what the value would have been just a little bit before that. And if it doesn't have access to that information, it can't make an accurate prediction. Because this value could just be anything, right? It has no context whatsoever as to what the stock price was before or what it will be after. So to solve this, we need to give our neural networks a kind of memory, right? Some way that it can remember what the past stock prices were so that it can use that data to make a prediction. And this is kind of like what we do, right? For example, if you have ever, I guess, gone outside, which, I'd say a fair amount of you have probably done that before, you'll know that a cotton candy piece is not the same as a cloud, right? Even though they look really similar, you know that because A, you can clearly see the difference, and B, that you have a memory, right? You can remember the fact that, okay, this is a cloud, this is a cat, this is a dog, whatever. Neural networks don't have that memory as of now. And they don't have that because if you give it a piece of if you give a neural network a piece of cotton candy as an image and you give it a picture of a cloud, it's going to think that both of them are clouds, right? Because all it uses is the features of that image. It doesn't actually know the context or anything. And we can do that because we have a short-term memory and a long-term memory. So this is exactly where long LSTMs or long short-term memory cells come in. These guys are absolutely awesome, and they help us give neural networks a brain, a true brain, so that they can remember past information. Now, it's a little bit more complicated than the regular cell perceptron that you might be used to, but the basic idea is the same. It basically uses the output of one layer as the input to the next layer. So let's think about this for a second. The way these cells are powered by is by 4 key gates. There's the forget gate, the remember gate, the learn gate, and the use gate. And each one of these is pretty self-explanatory. The long-term memory from the last cell, in this case is dog, right? This goes into the forget gate. And the forget gate has one job. It decides what information is useless and should be discarded from your memory and what information should be kept in it. and the information that should be kept in it goes into the remember gate, which remembers it for next time. So this would be updated dog, right? You pass in dog, the forget gate forgot some elements of it, and pass it into the remember gate. And it also goes into the use gate. And the use gate is your regular perceptron. This is where your updates happen. This is what we've been talking about for a long time. The learn gate, however, is a little bit different. The learn gate, basically what it does is that it takes the output from the last one. This one takes the memory from the last cell, and this one takes the output from the last cell. So whatever this use gate outputs becomes the input for this learn gate. And the learn gate passes its information into the remember gate and combines it with the forget gate. So really, this is acting like your long-term memory and your short-term memory, which I think is pretty cool, because this means that it can make decisions based on the context. So that's enough talk. Let's actually try building this stuff. So by now, I'm guessing everyone has access to this particular notebook, and yeah, let's just get started without any further ado. So here you might notice that we have a lot of different libraries, right? Way more than our previous workshop, which was like 2 or 3. So here, the only things we've added are pandas, and pandas is a data processing library, and we'll go into what this does more later on. And we've added Scikit-Learn. And Scikit-Learn helps us split our data into training data and testing data. Last time, we didn't actually need this library, because since we were using a dataset that was available from TensorFlow, it just did this automatically for us. But now, since we're using our own dataset from Kaggle, we need to import this. Next, we have Matplotlib, and this is just for plotting graphs and stuff, which will be really useful. And all of this stuff is to help us access the Kaggle database. So if we run this cell, and if you'll just click this button, it'll run as well. It'll take a second because the libraries are just a lot more, and it also needs to connect to the end server. And it should work. As you can see, it's on the first line right now. And you should see a message here that says choose to upload a file. And when it asks you for that, you click the upload button and you upload this file that we've just downloaded, right? And this is just a way for us to, yeah, right here. So choose files, right? I personally have this in the Innovire folder. So you want to find the kaggle.json file and you want to click open, right? So you chose that file and it will give you this message. And it should say downloading Tesla stock data from 2010 to 2020 zip to content. And if you guys want to check, you can click this file button here, and you should see the Tesla stock data and the Kaggle file right here. So let me know if you guys have that working. Does anyone have any thoughts or concerns, or is it working for everyone? Okay, Arush has it. How do you insert the Kaggle file? So I'll just run this. Wait, I'll just delete it from mine thing, and I'll do it again, just so you guys can see real quick. Delete file. Okay, so all you need to do is run this first cell. So click the run button here. It should take a second. And then it will say choose files, right? So you click choose file, you find wherever you downloaded the Kaggle API file, and you click it. So kaggle.json, and you upload it. And you should see a message that says downloading Tesla stock data from 2010 to 2020 right here. And if you want to double check that everything's working, just click this file button and you should see those two files here as well. So I hope that helped. Okay, cool. I think everyone's good now. If everyone isn't, just speak now or forever hold your silence, because this is the step 1. How do you insert the Kaggle file? It says no file chosen. One cell has been executed in the first. Okay. So did you run the cell itself or no? As long as you just click this button and click the upload button, it should function properly. Okay, that's interesting. Yeah, so Imran, how do you download the Kaggle file? It's right over here. I'll just send the link again in the chat. So just go here, click the download button, and then you should have the file downloaded onto your system. Go back to this file right over here. Run this library. So make sure you click the run button, otherwise nothing is going to work. and make sure that your Colab notebook is actually connected. So you should see RAM and disk and a check mark here. And once that's done, run it, and you should see a button that says choose files. Click that, choose the kaggle.json file, and you should download the dataset. Cool, so we will be moving on, but once again, if any of you guys have any questions or concerns, we can always stay back after. And I'll also be linking the solution version, which has all of the stuff we'll be writing today. Cool, so let's move on. Now first, we're going to have to actually load the dataset. And our dataset is in the form of a CSV file. So this is kind of like a spreadsheet, but we want to convert it into actual code so that we can read it. So pandas comes in really helpful here. So just run this cell, and you should see two interesting tables. So the first is a description of what the data is, right? And the second part is the sample of the first 5 rows of data. So as you can see, our data has the date, the opening value, which is the stock value when the market opens, the highest point it reached that day, in this case is $25, the lowest point it reached that day, and the closing price. The adjusted close basically is just the average of a bunch of different values. We don't really need to worry too much about this one. Then we have the volume, which is the number of shares that were, the volume of shares that was traded that day. So pretty self-explanatory. And here we have a description of what each one of those columns means, kind of. At least a numerical description of it. So you'll see count, which is the number of data points we have. This should be the same for all of them. We have 2,416 data samples, right? Next, we have the mean of each column, which is the average of each column. This is in scientific notation, but don't worry too much about that yet, because we will be scaling all of this down because the numbers are just way too high over here. Anyway, then we have the standard deviation, minimum, the 25% value, 50%, 75%, max, etc. Pretty self-explanatory, right? So now, let's move on. As we mentioned here, the data that we have right now is kind of all over the place, right? The minimum here is 16, but the minimum here is 1.185 and e to the 0.5. And this is a pretty huge value if you actually calculate this, right? And we can't really do data analysis when the data is so far apart. Like if you have a value that's in like 0.5, 0.6, and then you suddenly have a value in the next column which is like 2,000, 5,000, 8,000, the neural network is going to get very, very confused because you're passing in data that has different scalar factors, right? So if you pass in 2000 and 0.5, the 2000 is going to have a lot more impact on what the neural network does than the 0.5. So because of that, we want to scale all of these values to a small value, right? Ideally, maybe between 0 and 1. So that way, all of these values are within the same range, and it's much easier for the network to actually run. Not to mention that the network is faster as well. Now, you don't need to actually write this function since I've done it for you here, but you should understand exactly why this is working. So we're going to be using something called min-max scaling. And it looks more complicated than it actually is. So basically, to get, let's say for example that we passed in 19, right? So to normalize 19 between 0 and 1, first we would take 19 and we would subtract it by the minimum value of that column. So in this case, we have 19 and the minimum value is 16. So 19 minus 16 divided by the maximum value minus the minimum value. The maximum value, if we look, is 673, which is a huge range, right? So we would do 673 minus 16, and that would give us around 657. So 657 would be our divisor here. And ultimately, we would have 13 divided by 657, which would give us a value that is, of course, smaller than 1. So it scales our value properly. And we just do this for every single value in all of these columns, except for close. And we'll discuss why we don't do that for this particular column in just a little bit. So if we run this column, you'll see that suddenly all of our data is in between 0 and 1. And all of the ranges are nice and simple. So we've transformed that 19 to 0.0439, and we keep going like this until all of the data has basically been scaled. So this is actually pretty cool. We've gone from having literally 18 million in our volume section to just 0.016. Oh no, wait, sorry, that's the wrong one. To 0.36, right? This is just a description, this is the actual data. This is cool, because now, since all of our data is in the same range, This means that we can actually use it in our network in a way that's much faster and much more effective. Cool. Math is really helpful in machine learning. Now, this is pretty simple. We just split the data into training data and testing data. And here, this is exactly why we did not scale the closing column. See, we want our network to predict this stock price right over here, right? 944, 948. The thing is, if we scaled this value and we scaled it to a value between 0 and 1, it would give us like 0.5, 0.6, etc. But that's not even correct. That's not what this actual stock price is. So we can't scale that last column just because it would mess up with what the network is actually outputting. So we scale all of the input data, which, going back to what it was, we scale all the input data, which is like the date, the open, the high, and the low, and the volume. And we don't scale the output data, which is the close. And that's what we want our network to actually return. Pretty simple stuff. And we have a question, what does the volume column in the table represent? So the volume just represents the amount of shares that were traded on that particular date. It's just basically just the volume of shares, right? That's just what it's called in investing terminology. Nice. Keep going. So we split the data, and let's just print out the shape just so we know what our data actually looks like. All right, cool. So the shape of our data is that we have 1932 by 5. So pretty irrelevant, but usually in data science and AI stuff, it's a good idea to print out your data size shapes just so you have a good understanding of what numbers you're really dealing with. Cool. So we split our data between training and testing. Now it's time to actually create the model. And this one is going to be a little bit more complicated than our last one. If you'll recall, for the last one, we had a bunch of dense layers, right? Simple neural network layers. This time, since we're using an LSTM to give our network a little bit of memory, we need to use LSTM cells instead. And we also want a way to calculate what layer sizes we'll be using. As I mentioned in the last workshop, sometimes deciding layer sizes of networks is like the hardest part of developing an AI because it's almost random, right? Like I could easily make this number a 500 or 1,000 or 10,000, and really I wouldn't know how it would affect the X model. If my model accuracy is really low, like if I was getting 10%, I'm just going to keep randomly changing these values and not getting anywhere. Luckily, there is a way to determine what the ideal size for a particular layer is. Now, this isn't extremely accurate, it's more of an approximation, right? And it's in the form of this formula right over here, which we'll be discussing in just a bit. So the first thing that you want to do is actually write the input and output sizes, right? So let's do that right now. Sorry, I'm just finding the thing. Okay. So the input size is 5.1. This one, I just put it there for you guys just to avoid any confusion, since over here we have 5 columns, right? We're inputting 5 columns. 1, 2, 3, 4, 5. That's why our data set is 5. Cool. So let's start by importing a math library, right? And that's just to execute this formula over here. And we'll be discussing more about what it does in just a moment. So to do that, just click from math, import floor. And floor, all it does is that it rounds a number to its lowest point. So for example, if you got like 7.6 as your answer, it would round that to just down to 7. Or in other words, the floor of the decimal. So this is just to round the layer size. Because we can't have like a decimal as our layer size. And we are dividing here, right? So we might get a decimal. Cool. And now we'll be implementing this. So define a function. So type in def. And the function is going to be called calculate layer size. And it's going to take in 4 distinct arguments. The first is the number of input neurons. So this is basically our input size that we just defined here, right? And whoops, I'll just fix the spelling. Input neurons. Second argument will be the number of output neurons. And remember that the network we need to know this information because otherwise we don't know what the sizes of the middle layers are going to be if we don't know the input or output, right? So output neurons. And then we'll be finding the sample size, and this is just the amount of data that you have. In our case, it's 1932. We'll take the sample size, and we'll take the scaling factor. Now, the scaling factor is rather interesting because it's not set to an actual number, right? It's not actually important. The scaling factor is just a number that we choose randomly from 2 to 10 that just helps us to test out different combinations of layers. So you could set the scaling factor to 2, you could set it to 3, 4, 5, 6, whatever. And depending on how you set this factor, the actual value you're going to get for your hidden layers is going to change as well. So this is cool because now you only have to change one value as opposed to previously when you had to change the values for all of these different layers to find a different and good combination. So now that we've passed in our parameters, add a quick colon over here, and we're going to start making the function. It's pretty simple, right? First, let's find out the divisor. So when we're defining the divisor, A represents the scaling factor. Okay, so we'll do scaling factor. And if you guys notice, the scaling factor is being multiplied. So we'll just do a quick asterisk. And we notice here that we have Ni plus No. Ni represents our input neurons, and No represents our output neurons. So pretty simple stuff. It's just our input neurons plus our output neurons. So input neurons plus output neurons. Perfect. And this gives us our divisor, the thing that we're dividing ns, or the number of samples that we have, by. And we can just return this value. I'll return the 4 just in case we have a decimal, and we'll divide the sample size by the divisor. And this is a pretty nifty formula to give you a approximation of your hidden layer value. So, has everyone done this, or do you need more time? More time, please, okay. Does anyone else need more time, or is it just a couple people? Time, okay. Yeah, it's a little bit difficult to do the first time, right? But I guess writing out the code is probably the best way to learn things. So yeah. Cool. So I'll give you guys around 2 more minutes until like 3:36, just to write this part down. So in the meantime, I'll just quickly recap what we're doing here. Calculate layer size is just a function that helps us define the ideal layer size for our hidden layers. It's good because we don't have to just keep randomly adjusting them. And instead, we can just choose a scaling factor. And all we're doing here, even though this formula might look a little bit complicated, we're just taking the amount of data we have and dividing it by the scaling factor times our input neurons plus our output neurons. So pretty simple right here. It's just 3 lines of code. Cool. Is everyone done, or do we still need more time? Okay, 1 more person's done. I'll just wait for a couple more responses, then we can move on. Okay, cool. I'll just give 1 more minute, and then we can move on to actually building our LSTM. Cool, let's move on. So, once we're done this part, also Arush, I'll answer your question in a bit, just once we're done the workshop. Cool. So now that we've done the calculate layer size function, the next step is to actually build our model. And you'll recall that last time we had a different function entirely, right? We had dense layers, but this time we want LSTMs. So first of all, before we even define the layers, we need to actually call this function. We've defined it, but we haven't actually used it for anything. So let's call the function real quick. And first, we'll define a scaling factor. And remember that our scaling factor is kind of arbitrary. As long as it's in a value between 2 to 10, it doesn't really matter what it is. While I was testing it by myself, I personally found that a value of 4 works the best, But of course, feel free to test out whatever values you want and see how that affects the end network's accuracy. Then we'll define a variable called hidden nodes, and we'll run this function to get that end value. So we call calculate layer size, and we pass in our 4 arguments. We know that our input neurons are going to be 5, given that by the input size, so we'll pass in 5. We know that our output neurons are going to be 1, since we obviously just want 1 stock price and not like 10, right? This isn't a classification problem, whereas last time we had 10 numbers and we wanted to figure out what number it is, and this time we literally just want 1 value. So as a result, we're just going to pass in 1 for our output neurons. Our sample size, we know, is 1932, and that's why printing out data values is helpful, because you can see what the size of your data is. And we know that our scaling factor is just our scaling factor, so we'll just pass in that variable here. Cool. And now, before we actually build a model, I'll just do print hidden nodes, just so you guys can see what the hidden nodes actually are. So I'll run this file, and 80. Cool. So if we have a scaling factor of 4, our hidden nodes ends up being 80. And if I change this to 2 maybe, we'll get a different value. In this case, 161. So basically, the higher the scaling factor, the lower the amount of hidden numbers you're going to have, hidden neurons. In our case, I'm just going to set it back to 4, and let's continue building the network. So now that we know what our hidden nodes are, all we need to do is build our model, the same thing as last time. So we'll do model, we'll define what the model is, and then we'll just keep adding different values. Cool. So let's first specify the dropout probability, just because, remember, as I mentioned before, dropout is really helpful in making sure your network doesn't just memorize all the data. So let's do that. Dropout prob equals 0.2. Once again, this number is kind of arbitrary, but 0.2 is usually the best choice for this. All right. Now we're going to start adding our networks. First, the input layer. This time we want an LSTM and not a dense network. And our units, which is of course the size of that layer, is just going to be our hidden nodes, which we just calculated a minute earlier. Next, we're going to do a variable called return sequences. Now, this is interesting, and it might be unfamiliar to you guys because we've never seen this before, right? But return sequences, all it does is that it basically asks you, hey, do you want to return the memories for this particular layer, or do you not want to return them? And really, most of the time you should have this set as yes, because obviously, if we use an LSTM, we want the memories, right? That's the entire point. But for the last layer that we use, we're going to set return sequences for false, because the very last layer doesn't actually have to memorize anything, right? The last layer is just going to be the input of the layer that came before it. And this will be a little bit more clear once we actually build that part. So for now, we're just going to put in true, and we're going to specify our input shape as our, well, input size. Cool. And let's keep going. So that's one layer done. And now let's add in a dropout layer. Ideally, you want to add one dropout layer every single time there is an LSTM layer, just because sometimes LSTMs start memorizing things so much, you need one after every single time you use it. So this is pretty simple. We did this last time as well. Model.add dropout, and we set the probability of the network dropping out to dropout prob. And if you guys don't remember, what dropout does is that it shuts off parts of the network just so it forces the network to actually learn something. So they're pretty important. And after this, it's pretty simple. We can just copy paste the lines that we've just wrote, and we want 3 LSTM layers. Once again, this is kind of arbitrary, but I found that 3 is probably the most effective one. So we'll just add 3 more. And since only the input layer needs the input size, we'll get rid of this part in the next 2 layers. Okay, cool. All right. And remember that for this last one, we don't actually need return sequences, right? And why is that? Because the last layer is just one unit. It's not an LSTM, it's not something crazy, it's just one unit, and that's the stock price. So if it's just one unit, and it's simple, we can just use a regular neural network layer for this. So we can do dense, and we can set the units to just be 1. It's pretty simple stuff, right? And since the units are only 1, and we just need the stock price, we don't need to return the memories, because this layer can't even use the memories, unlike an LSTM. So we'll just set this particular one to false. And cool. let's add model.summary. And let's see what ends up happening. Cool. Now here, if you guys see, surprisingly our parameters are actually lower than our previous model. If you look here, we got 333,000 different perceptrons, right? This time we only have 129,000. But it's interesting because predicting stocks is more complicated in a way than actually predicting classifying a handwritten digit. So it's pretty amazing to see this. And you'll see a quick summary of what you've done. So there's our LSTM layer, which is our input. You have a dropout layer. You have your first LSTM layer, which is the hidden one, another dropout layer, another LSTM, another dropout, and our dense. As you'll notice, the layer size in our case happens to be 80, because that was the output of this calculate layer size function. So, that was a lot of information to take in. So, if you guys need any time right now, I guess now is the time to do it. Hidden nodes is not defined. So, remember that we have to do hidden nodes equals calculate layer size and pass in the different values. We actually have to pass in the functions. Sorry, we actually have to call the function. Oh, you did that. Interesting. So, are you sure that you wrote the function correctly? So, input neuron. So yeah, that's one of the things with coding in general is that you kind of have to go back and review your syntax and what you've done. So yeah. Oh, Aliza, you're missing a colon. So this is exactly what I meant. A lot of times in coding, you'll find that the errors are literally just because of tiny little things. Okay. So I'll give around 2 to 3 more minutes for you guys to do it. And I'll also copy paste all of this text in the chat, just so you guys can see what I'm doing. If you look at the workshop questions chat right now, the code for what I just wrote is in there. So you can copy paste this in that cell, right below the input size. So I'll give around 3 to 4 minutes, just because I know this was a lot of information to take in. And yeah, we'll resume back at like 3:47-ish. And after that, we're basically done. Once we've defined our model, next what we're doing is just the same thing as last time, which is compiling and testing our model, and we define something called a learning rate. Now, we didn't actually explain what this was, and I should explain it now because it's an important part. So, if you guys will recall, we had a graph last time, right? And that graph was how quickly the loss function changed depending on what the perceptron value was. So the learning rate is just telling us how fast we want to go down that graph. We want to take it in very little steps. Do we want to change the value from 21 to 20.999, right? And the smaller this learning rate is, the smaller changes we make. And this has a benefit as well as a disadvantage. The advantage is that it prevents you from going too far in any direction, right? Because let's say that there was a number, like let's say between 19 and 20, right? Where 19 was the lowest loss function, 18 was slightly higher, and 20 was the highest. So if you had 20 and your learning rate was set to something insane like 1.2, then it would just skip over 19 entirely and it would just go higher and higher and higher. Basically, it would take such large steps that it would miss the parts that go down in the first place. Because if you have it too small, then well, it might take a very long time for your neural network to arrive at an optimal value. And this optimal value is called the global optima. But of course, we'll talk about this in a little bit once this part is done. So, does anyone need any extra time, or should we move along and see how our network's doing? So, if you guys will look at what Eliza just posted in the chat, basically what you did is you printed out an object instead of the object's value. So, that's because of the code that we were doing earlier. The TLDR is that you basically printed out where that particular variable is stored in the computer's memory as opposed to the value itself, right? So when you define a variable, the computer has to store it somewhere in its memory, right? And it has a particular location for that. So since Google Colab uses Google servers to run, what it basically did is that it stored that variable at a location 0x7fc, that code that you see at the end, right? So if you just click print, it will basically print the location. So yeah, Arush, it doesn't need to say 80. We just did that briefly just to I just did that briefly just to show you guys. So I removed that print value at the end, just because it's unnecessary. But yeah, it's there just so you guys can see what the value is, and you can always add it in at the end. Cool. So I'm pretty sure most of you guys are done. So let's move on and let's see what happens next. So as I mentioned before, we define the learning rate and we set a checkpoint. Now, I didn't explain what this was last time, but I will this time because it's more important. So the checkpoint is basically how you want to save your models. So if you guys remember, last time we had different epochs, right? And we had different accuracies for each one of those. We had 33%, 67%, 81%, blah, blah, blah. And what we want to do is that we want to find the epoch that has the highest accuracy and we want to save that model file. So if you notice, we actually saved a lot of models in our last one. Right? We saved 1, 2, 3, 4, 5, all the way up to 25. Right? And we skipped a couple in between because those accuracies weren't high. So in this one, we just want to make sure that we save the best model only. This is set to true. This just tells us how exactly we want our models to be named. In our case, it's going to be model, whatever the loss of the model was, .h5. So pretty simple stuff. Next, we define our loss function. Our loss function in this case is going to be our mean absolute error. At Arush, it is possible to save all models, but that is a very bad practice, just because most of your models aren't going to be optimal accuracy. Right? Only one or two, or, well, it depends on how much you're training it, but you only want to save the models that are the best ones. Because otherwise, if you have a bunch of models that are lower accuracy, they don't really have much use. But it is possible to save all models. I wouldn't recommend it though. Cool, so let's run this file, and we defined our loss function, or our inspector. And next, now this part is a little bit, this depends on what you guys want to do. So we have two options right now. I already went through and trained a model that is really good at predicting Tesla stock. And that one is loss9.h5, right? I particularly named it that because the loss is, well, 9. And it's not actually here, the link to that file, because what we're going to do is that we're going to try and create our own model, a model that is different, right? And then what you can do is that at the very end, when we're done running all the cells and everything, is that I'll give you the link to this model, which is actually pretty high accuracy. And what you can do is that you can see how your model compares against the one that I trained. But for now, we won't be using this model, and we'll instead try to train a brand new one. Now, this is going to take a little bit of time, because we've specified our epochs to be 100, and because our data is a lot more complicated than it was last time. So when you run this, this might actually take quite a while. And in fact, most deep learning models often take days or weeks of training just to actually get a good model, which is probably the biggest part of machine learning. So let's quickly run the train model thing. Remember, do not run the loss9.h5 file. You will get an error because we don't have that file yet. So first, our loss is insane. It is literally 194, right? And that is like infinitely higher than anything we ever got. Like we had 2 as the maximum one here, right? This time we're getting 196 if we scroll above. And that's why we need more epochs, just so the neural network has more time to improve. But as you can see, our model is slowly improving. We went from 194 all the way down to 173. And now, if we look at where the model is right now, I'll scroll real quick. Right now, we're at 162. We even hit 157. And ideally, the more you go down and down and down, the better your model will get. So we're on model 85, 150, 160, and we'll hit 100 at one point. So our loss is 162, right? And we'll see that, okay. And the next one, the next cell just plots this out, just so you can see a visual representation of how your loss has changed over time. So I'll run that quickly. But we might notice a slight problem here. And that problem is that, of course, our loss is still pretty damn high, right? So there are a couple of ways that we could go around solving this, because this happens a lot of times in machine learning. So the first thing you could do is go and improve the number of, go and increase the number of epochs that your model is training for. So instead of doing 100, you might do 200 or 300 or 400, right? Something absurdly high so that your model has a longer time that it can train for. The second thing is, well, first let's look at this graph to see if we can find anything. Now this is rather interesting. as our epochs went on, as time went on, our training loss decreased, but it decreased in huge spikes. So instead of going down like a nice line, kind of like what we saw here, right? And this was our accuracy. So our accuracy went up and it kind of, shook a little bit, but it was still pretty consistent. Here we have a huge spike. Right? And that's because, of course, our data is a lot more complicated. And because we're using LSTMs, which, since it has memory and all of that stuff, it is a lot more complicated than what we originally have. So here, what we basically see is that our testing data, sorry, our testing loss is roughly the same. It is decreasing, but it isn't decreasing by all that much. And our training data is just spiking like crazy, right? So this is where you might say that, hey, you know what? It looks like our model isn't learning that much, so maybe we can change our scalar factor, right? And I won't actually do this right now, but feel free to play around with this. You might change this to 8, or you might find 2 to be nice. And then you keep testing it, and you see how this loss changes over time. And you might even adjust the epoch value, right? Instead of doing 100 epochs, you might do 200 or 300, just to see how it changes more over time. And ultimately, that's really what deep learning is all about. It's about making decisions about the best way to train your model to get it to represent some data. So right now we have this one, and this cell, what it does is that we will take actual Tesla stock price and we will compare it with our model's prediction. So right now, it doesn't look like our model is that accurate. The loss is still well above 150, so it should be a pretty crazy prediction. And as you can see, it really is. The actual Tesla stock price is like this, and our model is just predicting the same value over and over again, which is just absolutely nuts, right? So this means that our model literally has not been trained at all, which that explains why our loss is so high. It has gotten better, but it's still absurdly high to actually do anything. So now, what I'll do is that I will link since we're done, I'll link the loss H9 file, which is the model I trained after a couple hours that I found was pretty accurate, and it actually matched the actual stock price pretty well. So the model was able to predict effectively what the end stock price would be. So that's right here, and I will send that in the workshop questions chat real quick. All right, cool. So all you need to do now, one second, I'll just wait for everyone to come on, and you'll see that the completed model that I trained, the one which has a pretty high accuracy and low loss, that's right over here. So feel free to download that file, and once you've downloaded it, go back to your to the workshop notebook, click the file icon, click upload right here, and then choose that file. So I have that saved right here into my Innovire folder, so I'll click it, and I'll upload it. And this is just a quick reminder that it doesn't actually save the files, so if you have a model that you really like, make sure to download it from here, since this is all stored on Google servers. So I'll click upload real quick, and I should see loss 9. When I try playing the training model, it says my X-train is not defined. Yeah, so just make sure that you're running all of the cells in the correct order, right? So when you're running this notebook, you want to go all the way to the top, and you want to run every single cell. So remember, you click here, you want to run all of them, especially this one, because, sorry, this one right here. So X-train and X-test are defined in this cell, the one where we split the data into training and testing. If you run that cell, it will define those variables as well. And just to answer Arsh's question, how do we upload the solution and train model? So just quickly remember that go to the solution included hackathon resources, which I just linked in the chat. Go to this particular link right here, download the loss9 file. Then, once you're back inside, click upload. So first click the file icon, then click upload, then click loss9.h5. Upload it, and you should be good. And once you've uploaded that file, go all the way back here, right above the training function. This is the one that we didn't run last time because we didn't have the model. But now we do have the model. It's saved in our files. So we can run this, and it will load our loss9h5 file into our model variable. So we run that. And since this model is already trained, you guys don't need to train or do anything, right? All you need to do is go all the way back down to our, see, that's the disadvantage of having 100 epochs, takes forever to scroll, but you can go all the way down and compare to see how this data changed with the actual stock price. And this is actually insanely accurate. You see that this very closely is able to mirror, I'll just zoom in just in case you can't see a little bit. the model that I trained before is able to very closely mirror the actual stock price of Tesla, all the way from example 0 to example 2500. And while it wasn't able to predict these tiny little spikes, it came pretty close. This was a lot more accurate than the previous model, which literally is just like screw this and outputted just a straight line. It wasn't able to predict this end spike at the end, but honestly, given the fact that it was able to predict the majority of the stock fluctuation pretty damn well, I think that we can actually classify this as a success. And that's insane. The fact that we just built and developed a model that literally is able to mirror Tesla's stock price with pretty high accuracy. And what's even better is that even if it's not able to predict extreme highs and extreme lows, it came pretty close. I think that even if we were able to use this model in the real world, for example, it would have an insane amount of utility because it would be able to save money for thousands and thousands of people who are trying to, well, just make some money. And yeah, that is pretty much it for this workshop. So before we wrap things up, does anyone have any questions, thoughts, or concerns about this? And once again, feel free to speak it out loud or just drop it in the workshop questions or workshop chat channel. Oh, Imran says he wasn't able to download any of the files. So remember, all you need to do is go to the link, click the file name, then once you arrive to this particular page, click download. That's pretty much it. I'm not sure okay. Okay, cool. So I'll take one question at a time. So we have a question from Aisha. Could you recap what each one of the columns represent? Okay. So for those of you guys who don't know, her question is basically about the normalization that we just did. So right over here, this was the first 5 rows we printed from the Tesla stock dataset. So the date, pretty self-explanatory. This was the date that was recorded. Now the open value, right over here, actually this is the scaled version, I'll go back to the actual data. The open value is what the stock was at when the day started. So remember that the market opens from 9 a.m. to 5 p.m. So 19 in this case was the value that Tesla stock was trading at when the market first opened on that particular day. The high is the highest value that stock reached on that day, the low is the lowest value it was on that day, and the close at what price the Tesla stock was when the day ended, or in this case at 5 p.m. So that's pretty much what it is. And volume is just the amount of stock that was traded, and that's pretty much it. Cool. Okay, next question. How do you open the train model? Okay, I'll just go over this again very quickly, just to not, I guess, bore everyone else. Really, really simple. You go here, the solution included resources, which I linked in the workshop questions chat. You open the file, and eventually it will say download right here. You click the download button, and then once you have that downloaded onto your system, you go back to the stock predictor, and you click the file button, and then you upload the file that you just downloaded. So I already had that downloaded, so it's right here. And then once you upload it, you go all the way back up here, where it says model equals load model and the model name. So this just saves the model that you just downloaded into the original model. And once you run that, you can just test the model and see what its accuracy is by running this last cell over here to see the stock price versus the predicted ones. Cool. Let's take some more questions. Cool. So does anyone have any more questions, or should we, I guess, say some closing remarks? These can be questions about anything you want, whether it's about AI or just things in general. So yeah. Actually, there was a question we didn't answer before. This was, I'm not sure who it was by, but there was a question that asked, are stock indicators like the RSI indicator types of AI? The answer is no. So RSI indicators, for whoever asked that particular question, they don't, they basically do a technical analysis, right? So they use purely statistical ways of finding that, but they don't use AI. So they don't use neural networks. They use other types of algorithms to solve their problems. But that's interesting though. Definitely check RSIs out if you are interested in that kind of thing. Cool. And I think there was another question by Arush, if I'm not mistaken. Uh, hmm. Yeah, does anyone have any other questions, or is that it?
Well, actually, we do have a question from the presentation. And that question was actually, I feel like that's something you could answer, Aditya. So I'm gonna go ahead and read that out to you. Allow me to just find it. Yeah, so Manasvini she asked, what softwares are good to use for coding in general? And I think
Okay,
that
so yeah.
you give us your 2 cents on that, Aditya.
Definitely. So coding is done in IDEs, integrated development environments. So Colab is not really an IDE, right? Google, the software that we're using right now, I'm just using it just so that we can all make copies and everything, because Google is amazing for that. What I personally use is VS Code, and I think that most people use that as well. So I just opened it up right here. VS Code is probably like the most used IDE from what I've seen. This is just some code I was writing earlier, and it's pretty cool, right? You have an Explorer, you can download different extensions and everything. This is usually how I code stuff, and that's what I would recommend to other people as well. But really, you can use anything, right? If you don't have access to a Windows computer, then you can also there's also something called rebel.it, and this is pretty cool because it allows you to test code online. So you can just click start coding and you can sign up, and it's basically just online IDEs, and it's pretty fun. The reason we didn't use that right now is that you can actually do AI stuff in rebel.it, so that's a disadvantage. Cool.
So
Uh,
Manasvini,
there-
sorry, Manasvini, there's your answer to your question. VS Code is a good one, so is REPL.it. Thanks, Aditya, for answering that question. But I think with that, we're kind of, oh, it says here there's
we
another.
have a couple more questions. I'll just read them. Do you think that Scratch is a good program to have fun in? I mean, Scratch, I personally also started programming from Scratch as well, so it's a little bit of a soft spot. Uh, but yeah, Scratch is fun. It's good to give you an intro to coding, especially if you don't have experience before. So that's definitely something I'd recommend. There's also a question from Arush earlier that I didn't answer, but I'll just take it now. This is a bit of off-topic question, but what company do you own? So I personally run Krista, and that's a company that I've made in the last months. The goal of that is to improve customer student productivity, right? Basically to give you insights on how efficiently you work, your most productive and your most creative times, and also just to help you work in general. Like recently, we've added a Pomodoro timer, and we're also adding tasks lists. Just like an all-in-one hub to be productive, which is what the goal is. Cool. Any other questions, or we can just end it off right there?
Like to give my 2 cents on the Scratch question. So do you think Scratch is a good program to have fun in? I think Scratch is actually a really good intro, as Aditya said, because it really does teach you the logic behind coding. So even behind script, because in Scratch you can view it in either block form or script form. But no matter which way you view it in, I feel like it does a really good job at kind of helping you understand what the logic is behind writing a code. Like whether it's like if statements or all these things, like Scratch really helps you understand the basic logic. And it's also obviously it's really fun because you get to play games and make your own games. So I definitely think Scratch is a good program to have fun in and to learn in general. But with that, I think we're mostly for today. We are done. We covered the